Okay, so we're jumping in 9.4. I'm going to write this one out a little bit more just because there's a lot of definitions for this one. Um, so here we go. First off, definition here, autonomous differential equation. An autonomous differential equation is a differential equation for which the derivative dy dx is a function of only y. In other words, when you do have your differential equation, so y prime is equal to something, you are not allowed to have x's on this right-hand side. They can only be y's of some kind. Okay. All right, cool. A little bit more definitions here. I don't know what to call this one, just definition. If y prime is some function of y, we'll just call it g of y for now. So if this is an autonomous differential equation, then the values of y for which the derivative is equal to 0 are called equilibrium values, or they're also called rest points. So in other words, if you look at the right-hand side of a differential equation that is autonomous, meaning it only has y's in there, and you solve this for 0, these are what's called the equilibrium values or the rest points. As far as like real-life word problems go, these are going to be the values that don't change. Like a good example would be something called terminal velocity, if you've ever heard of that. So if something is falling and there's air resistance, eventually it's going to reach what we call terminal velocity, which means it's never going to get any faster or slower. It's just going to stay the same speed. That's called an equilibrium value because once you're at that value, once you're at terminal velocity, you're not going to change. So that's just kind of an example of what we're talking about here by equilibrium values or these rest points. Okay, a little bit more with these. So I already said that. Phase line. So this is the whole point of this section, these phase lines. A phase line is going to be a plot on the y-axis that shows the equation's equilibrium values. Okay, cool. And that's what we're going to be doing here. So going back to my pen, let's go through an example. And I'll break it down into steps. So what we want to do is we want to draw a phase line for the differential equation dy dx, or y prime, is y plus 1 times y minus 2. Okay, and again, we'll write steps here. All right, so the first thing that you want to do is to just draw a number line. This number line is representing the y-axis. And then the next thing that you want to do is you want to plot the equilibrium values. The equilibrium values are pretty easy for this example up top because it's already factored. So the two values that are going to make that to be 0 are going to be -1 and +2. So we'll plot those on the line as well. Okay, the next thing that you want to do, and you could wait to do this step until a little bit later, but we'll go ahead and do it now, is we want to identify where the derivative is negative and positive. So if we look on our number line here, I'm just going to copy it below. Our number line is split up into 3 different intervals. Everything below -1, everything between -1 and 2, and everything above 2. Remember that at -1 and at 2, the derivative is 0. So these are going to be the points where it changes from decreasing to increasing or increasing to decreasing. All right, so all we do is just plug in values. So let's just pick something that is below -1, and we'll plug that back into the differential equation. So if I plug maybe -2 into here, -2 plus 1 is -1, -2 minus 2 is -4. I have a negative and a negative. Those will multiply out to be positive. In other words, in this section, my derivative is positive. Okay, and I'm not going to bother doing the others, so just plug in maybe 0 up top. You'll see that the derivative comes out to be negative, and then plug in something bigger to 2 up top. You'll see that the derivative comes out to be positive. There is another way to rewrite this if you don't like writing it like this, with the values up top, and that's by writing arrows. Here, because my derivative is greater than 0, that means my function is increasing. So it's going to be going up to the right here. In between, it's decreasing. Above 2, it's increasing again, so it's going to the right. Okay, the next thing that we want to do, not only do we want to figure out where the function is increasing and decreasing, but we also want to find the concavity. So to do that, we're going to calculate the second derivative and mark the intervals where not only is the first derivative positive or negative, but where the second derivative is negative or positive. So let's talk about finding the second derivative first, because it's not as easy as you would think. So let's say that we have our differential equation here. I wrote it wrong. It's supposed to be y plus 1 and y minus 2. Let's find the second derivative. To find the second derivative, we're going to have to be careful because we're going to have to do some implicit differentiation stuff. So what I'm going to do is I'm going to go ahead and multiply out that right-hand side just by foiling them together. Then we'll take the derivative of both sides. When I take the derivative of the left-hand side, y prime is just going to go to y double prime. But when I take the derivative of the right-hand side, remember that we're really taking the derivative with respect to x. So then when I do the derivative with respect to y, or not with respect to y, but when I do the derivative of y, we're going to have to do an implicit thing. So I hope you remember this from Calc 1. Take the derivative of the outside function, that's going to be 2y, but then we have to multiply by the derivative of the inside, so a y prime. Same thing with the next one, negative y has derivative of negative 1, but then negative 1 we're going to multiply by y prime. Negative 2 is just going to go to 0 since it's the constant. Next, what I'll do, since I have a y prime on both of these, is I'll go ahead and factor it out. And I actually know what y prime is, because remember, y prime is y plus 1 times y minus 2. So that I'm just going to substitute in. And what I've done is I've now solved for the second derivative. Okay? Before we do anything, we do want to set this equal to 0. So if I do set this equal to 0 and solve, I'll get 3 different answers this time. 1/2, negative 1, and 2. Which means that when I draw out the number line, I have the negative 1. I'm also going to have a 1/2, and I'm going to have a 2. I have already figured out where the first derivative is positive and negative in these intervals. Remember, for the first derivative, we had positive here, so it's going to the right, negative here, positive here. So that was just copying it from above. Let's also figure out what the second derivative is in these intervals. So again, pick a number less than negative 1 and plug it into the second derivative. So if I plug negative 1 into the second derivative, I end up with a negative number, negative number, negative number, so it's all negative. 3 negatives make a negative. Plug a number in between negative 1 and 1/2. This ends up being positive when you plug it in. In between 1/2 and 2 ends up being negative. Bigger than 2 ends up being positive. A lot of times students ask me, is it always going to alternate like that? And the answer is no. It is not always going to alternate negative, positive, negative, positive. Okay, but now that we have this, we're allowed to sketch solutions. This is what we call the phase line. But with this phase line, I can actually graph what potential solutions are going to look like. So if I look at the XY axis, I have a couple of interesting locations. Negative 1, 1/2, so if this is 1, then 1/2 is halfway, and 2. At the 2 and the negative 1, these are those equilibrium values. So I'm just going to draw horizontal lines there, because if I do end up on one of these lines, I'm just going to stay on that line. The 1/2, I'm going to draw a dotted line at, because this is not an equilibrium value, but this is going to be an inflection point because the concavity changes. Okay, now let's look at each of the different sections. I have everything below the -1. Below -1, I have increasing and concave down. Increasing and concave down looks like this. So all of the solutions below -1 are going to approach -1 from below and then stop. All right, in between -1 and 1/2, I am decreasing and concave up. And then between 1/2 and 2, I am decreasing and concave down. So in between -1 and 2, I'm decreasing the entire time, but then I need to change from 2 going down to -1, I'm concave down and then concave up. So the solutions are going to look like this. And then as soon as I hit that 1/2, I need to change to be concave up instead. So those are all possible solutions between -1 and 2. Finally, above 2, I am increasing and concave up. Increasing and concave up are solutions that look like this. Depending on your initial conditions, whether you start below -1, in between -1 and 2, or above 2, these are the paths of the solution curves. One last thing I want to say here are the type of equilibrium values that we have, and I forget what they're called. This one is called, oh, I remember, stable. Unstable though. So 2 is an unstable equilibrium because as time progresses, every solution goes away from it. -1, on the other hand, is called a stable equilibrium because all of the solutions eventually come down to be -1. Okay, cool. But this phase line, as long as it's an autonomous differential equation, allows us to graph these sketches based on the phase lines.